Okay, we are in our geometry. This is lines of symmetry and composite mapping today. This is Unit 2 transformations. First thing we're going to talk about is line symmetry. Line symmetry happens when a figure has line symmetry if the figure can be mapped onto itself by a reflection in a line. So when you're thinking about this, it's like the mirror image. So if you could draw a vertical, horizontal, diagonal line, and the picture maps onto itself. For example, if I draw a vertical line right here, and you folded that picture in half on that line, this corner maps directly onto that corner. So that is when you fold a line in half, that's called line symmetry. The picture folds exactly on top of the other side. Point symmetry. If the figure is mapped onto itself by rotating the figure 180 degrees about a center point. So, when I talk about a center point, it means the middle of the picture kind of thing. If you were going to spin that or rotate that, it means it looks the same upside down, basically. If you spun that around, this would come all the way over here, and it would be the same. So if I took my paper, I'm going to turn it upside down. This picture still looks like an N, whether it's upside down or right side up. Spinning at 180 degrees creates the same picture, so that's point symmetry. Rotational symmetry if the figure is mapped onto itself by rotating the figure less than 360 degrees about a center point. So in this case, if you were going to rotate around that center point, it's like a pinwheel. It spins, and you can see, like let's say here is your starting point, okay? You start right there on this triangle, and you spin clockwise or counterclockwise, it would just spin to here, and it would be the exact same picture. Or it could spin to here, and be the exact same picture. So rotational means it can rotate any direction, any amount of degrees, and it will fall onto itself. Later we're going to talk about how many types of rotational symmetry. So like this first one has maybe one line of symmetry, because if you drew a diagonal line this way, it doesn't fold in half, or a diagonal line that way, it doesn't fold in half, but vertically it worked. So it had one line of symmetry. Rotational symmetry, it either can rotate 180 degrees or not. But it's point symmetry. Rotational symmetry can have many different. So if you rotate this, this would have 1, 2, 3, 4, 5, 6, 7 rotational symmetries before it gets back to the top again, or 8 if you want to include back to the top. So we would accept either of those. So example 1, we're going to look at some pictures and check mark, do they have the following? Is it line, point, and or rotational symmetry? Check all that apply, and then we're going to try to determine how many of those would have. So line symmetry. Could you draw a line in this picture and it fold in half and get the same picture? So, like for instance, if you draw a line across here, that's for sure 1. If you drew a line here, this would fold over here, same thing here. So that's at least 3 different lines that we figured out. But could you also do like this line here, not in a corner? Could you fold a line in half here, and the left side fold over onto the right side? That would work also. So if you were to do this on all the sides, there would be a total of, I'll check line symmetry, and there would be 6 lines of symmetry on that. You can do lots of diagonals there, or vertical or horizontal. Point symmetry would mean I can rotate this upside down and it will look the same. So yes, there is point symmetry. Rotational symmetry means, okay, if you start here, let's say I start on this side. If I was going to rotate this, how many times could I rotate it till it got back to the same position and it's mapped onto itself? So 1, 2, 3, 4, 5. This only works because this is an equilateral, meaning all the sides are the same length. So that we would say this has rotational symmetry, and by the 6th time, you can either say 6 because it takes 6 turns to get back to the beginning, or we could say it has 5 rotational symmetries because 1, 2, 3, 4, 5 before it can get back to the top. Okay. Let's try the next one. This is an equilateral triangle, means all the sides are the same length. Line symmetry, yes, it has line symmetry. You could draw a line either from a point to a side. There are 3 lines of symmetry in this one. Rotational symmetry, this one does not have rotational symmetry. If you rotate this 180 degrees, the flat part would be at the top and the pointy part would be at the bottom. So it doesn't have point. It does have rotational symmetry though. You can rotate, say, this point or that side 1, 2, it would take 3 turns to get back to the top. So let's say this picture over here takes 6 turns to get to the top. This one would take 3 turns to get back to the top. Okay, this is a parallelogram. Line symmetry means, can you fold this in half anywhere and it creates and maps onto itself? If you did vertically, say here's a line, this side would be longer than that side, so it won't match if I flip it that way. If you flipped it diagonally, it would crisscross. That would come down here, this would go up there, so that way doesn't work. It also doesn't work horizontally. This side would flip down here and that would go up there, so that doesn't work. So there is no line symmetry in this one. Point means if I turn this paper upside down, will it look the same way? Let's try it. So I think that looks the exact same as if it was up this way, so we will say it does have point symmetry. So it's going to automatically have rotational symmetry, it's just how many times does it rotate. Let's see, if I rotate 90 degrees or 1 turn, it's not going to be the same. It has to rotate 2 times to get back to the original. Alright, line symmetry. If you drew a line anywhere on this problem, would it ever map onto itself? No. Will this picture look the same upside down? Nope. Can you rotate it and it land on the other side? Nope. So this has no symmetry at all. So let's look at this one. Line symmetry. I can draw a line here, and this would flip to there. So yes, it has line symmetry. Let's see. How many lines? We could draw in a bunch of lines and see. That was there, that was there. Makes sense. Okay, so we should have 5 lines of symmetry. Point symmetry, I would say no. Because if you rotate this, this point would be down here and there's no point down here. 180 degrees is upside down, so nope. It does have rotational symmetry. We can rotate and it does spin and fall on top of itself, but that's not at 180 degrees. So let's say we start here, we would have 1, 2, 3, 4, 5 rotational symmetry. Alright, last one. Line symmetry. It doesn't seem to be anywhere I can draw a line that it will flip exactly on top of the other one. Point. If you turn this picture upside down, it actually looks exactly the same, which means it has rotational symmetry as well. Alright, let's look at the next page with composite mapping and what that looks like. Composite composite mapping is a fancy way to write out. We did this a little bit. We called it the rules with translations. Composite just means you're going to do more than one type of translation. It's like a multi-step problem versus a one-step problem. So when you reflect over the x-axis, you take a picture and reflect over the x-axis, it actually changes your y value. So it's the opposite of y. We also call that a vertical reflection. So because you're going vertically, you're flipping it down. Over the y-axis would be going left to right or right to left. So that's going to be the opposite x value. And that is called a horizontal reflection. When you stretch something horizontally, that's going to make it wider. So that part up here is when there's a number with the x. When you stretch something horizontally, that's right here. Okay. When you stretch something vertically, that is the number in front of the y. It's like kind of like the scale factor thing, where you times something by the x. You could say the x gets so many times bigger, or the y gets so many times bigger. And a translation is what we did the first day. X plus h, y plus k. Okay. Those should be familiar. Rotations are something I just want to put on there just as a review, but our rotations for 90 degrees counterclockwise was negative y comma x. 180 degrees was negative x, or opposite x, opposite y. And then 270 was y comma opposite x. Okay, so we're not really worried about the rotations today with these composite mappings. We're really talking about, was there a reflection, a dilation, or a translation? Do you remember the only thing that changes the size or shape of a figure is the dilation? Okay. So example 1, describe the changes made using the following mapping rule. Then give the coordinates of the new image. So we're going to break this down. Try and do my best to simplify this. The first thing you see is 3x. So this 3, let's put a little dot over here. The 3 stands for if you look up at the top, that's a horizontal stretch. Because it was affecting the x value. Then you have the +7. That's called a translation. So I'm just going to kind of underline this here, x plus 7. That part would mean, so the x plus 7 part represents right 7. That's from our translation part. And now let's look at the y part. On the y, you have a 2 in front of the y. So this 2 with the y means vertical stretch. Because it's twice as big vertically. And then this part here, the y minus 1 represents the translation. That would be down 1. Okay. So the x plus 7 and the y minus 1, those are translations we did on day 1. The other things, the numbers in front represent stretches of some kind. So it's like taking it, times it by 3, or timesing it by 2. So basically, to find the new ordered pairs, you plug in your value for x and your value for y into like that formula. So if I was going to do the x, that would be 3 times 3 plus 7, comma, and then if you were going to do the y, that would be 2 times 2 minus 1. Just using this is x, this is y, plugging it in place of the x and y. So this would be 9 plus 7 would be 16. And 4 minus 1 is 3. So this would be the new image. We'll do the same thing with these numbers. 3 times negative 1 plus 7, comma, 2 times 0 minus 1. Plugging in your x value and your y value. Negative 3 plus 7 is 4. 0 minus 1 is negative 1. So this would be my new b value. So describe it and then find the new ordered pairs. Why don't we look at the next one? Describe the changes made. Okay. So this one doesn't have a number in front, it has a negative sign. So if you look up at the top, a negative sign in front of the x means it either flips over the y-axis, or I like to think of it, since this negative sign is with the x, I just call it a horizontal reflection. Okay, a negative sign means horizontal reflection. The next part you see is the x plus 1. On the x-axis, if you go plus 1, that would be right 1. And I'll go ahead and do the y plus 3 means up 3. It didn't have any negatives or numbers in front of the y, so there's nothing else besides we have a horizontal reflection because of the negative sign. And the x plus 1 is right 1, y plus 3 is up 3. Now plug in your numbers. So this is a negative sign, and then I'll put the x value as 3 plus 1. The y value is 2 plus 3. So my new a value would be negative 2, 5. Same thing you're going to do with the next point b. You're going to plug those numbers in. On this one, if you have a negative sign and then you plug in a negative 1, you can do this a couple different ways. Knowing that we had a negative sign and I plugged in a negative 1, two negatives should make that become positive 1. Okay, so your answer should be 2, 3. And that's the new b value. As when you have, this is like the opposite of whatever it is, so the opposite of negative 1 made it become a positive 1. Alright. How about you guys try the next one? Oh wait, nope, we're going to try this one together. This one says, using the mapping rule to identify the pre-image. So this time, instead of giving you the rule and just plug it in, you're actually working backwards on this. So this is the new a value, and this is the original problem. It says, use the mapping rule to identify the coordinates of the pre-image. So we're going to take 4x minus 1. We're going to do the a's first, okay? So 4x minus 1 equals 3. That's the x value. And this whole thing represents the x value in the new image, okay? So to find the original one, you're going to solve for x. And you're going to do the same thing with the y values. This is your y value. So 2y equals 1 divided by 2. So my original image was 1 and y was 1/2. Okay, so you just take the formula and you set it equal to the new value and solve to find the original one. Let's do the b one on your own then. And I don't care if you write decimals or fractions there. I just did 7 divided by 2 is 3.5. If I put it back on the line, I wrote it as 3.5. It doesn't really matter. Alright, on example 4, you're given two ordered pairs and a description. It wants you to write the mapping rule for this one. So using what information they give us, we are going to try and write a mapping rule. So I'm going to highlight, it says translate down to and write 3. So let's just do that part first. When you write a rule, you always start off with x comma y and then the arrow to show I'm changing the x and the y. And I'm going to leave some space here because I don't know what else is going to go in here, but right 3 would be x plus 3, and down 2 would be y minus 2. Okay, let's see if there's anything that needs to go in front of that. It says, and reflect over the x-axis. So you got to think, if you reflect over the x-axis, which value does that change? Let's pretend this is our x-axis. If I took a picture and I flipped it over the x-axis, that would change its y values. So you want to put a negative sign here because that would imply reflecting over the x-axis. Changes the y value. So this is because of the reflection. Now use your rule that you've written, then give the coordinates of the new image. Okay? So let's see, we're going to use our point. The new A would be 3 plus 3, and then negative 2 minus 2. The new A value would be 6, negative 4. Okay, now let's do the B value. So the B value is 5, so 5 plus 3, and the Y value is 9, so negative 9 minus 2. So my new ordered pair for B would be 8, negative 11. So if you were to graph the point 3, 2 and did all that transformations, then you would come out to the point 6, negative 4. Are these two segments, the pre-image and the image, congruent? So let's look back. A translation doesn't change the size, and a reflection doesn't change the size. So I would say yes, they are congruent. Because translation, oops, I didn't need a comma there, because translations and reflections do not change the size. Okay, so now we have another one. This one says we have segment AB is translated based on the mapping below. Describe what happens in this transformation, then give the coordinates of A and B. Are these two congruent? Okay, so you're going to look and see what's happening in this one. Let's do, it doesn't matter where you start. I sometimes like to start if I see a negative sign. So, and the first thing I see here, there is a negative in front of the X, so I'm going to say that is a horizontal reflection. Or you can say a flip over the y-axis. Next thing I see is a number 1/2. So I'm going to say this is a horizontal shrink. It's getting smaller. It's half the size. Then I have the part x plus 5. So I'm going to say that means it moves right 5. That's everything with the x's. Now let's look at the y values. We have a negative sign in front of the y, so we're going to call that a vertical reflection. Then we have no number in front, but we have y plus 3. So that would make the graph shift up 3, or translate up 3. Alright, so we're going to take and describe what happened, check, and then give the coordinates of the new image. Alright, so the new A, if you plug in the number 4, it would be negative 1/2 times 4 plus 5, okay, and then negative 11 plus 3. So the new A, that would give me negative 1/2 times 4 is negative 2 plus 5 is 3, negative 8. Okay, now you want to do the same thing with the B's. Didn't really leave enough room there, but the B value would be plugging in negative 1/2 times 8 plus 5. And this one we'd have negative 9, so I'll just say positive 9 plus 30. So negative 1/2 of 8 is negative 4 plus 5 is 1. And 9 plus 3 is 12. Alright, so that is everything related to describing it, finding new points. Are these two images the same? In this one, I'm going to say no, because there was a horizontal shrink. Alright, so that is everything. So, this is a little box you might want to study as far as studying goes. If it's a negative y, we call that a vertical reflection. If you have a negative x value, we call that a horizontal reflection. If you have a number with an x is a horizontal stretch. A number with a y can be a vertical stretch. You can also have what's called a horizontal shrink or a vertical shrink if it's a fraction. And a translation is when you add or subtract numbers.